Okay, so we mentioned next week we'll have the midterm scheduled, and now you should see the midterm study guide posted on D2L. And I'm going to also send you a copy to the chat. It's a PDF document, and basically the study guide contains a list number of questions go by, basically the syllabus, the different topics. So, for example, on the first day, we covered a number of things. So for the midterm, it's going to be take home, and there will be multiple choice, true or false, and short answers. You can do, basically you can take the D2L quiz anytime between this coming Saturday through the end of next Sunday. So from the 20th to the 28th. It's going to be a timed D2L quiz, a single attempt. You will have 1.5 hours. So speaking of, this time and also the format, I know it's open note. However, since you only have 1.5 hour, 90 minutes in total, and also it's going to be forced shut down after you pass this 1.5 hour. So I would still carefully review. So just it's take home, but you will want to review carefully before you take the quiz, because I don't think you'll be able to check everything as you take the quiz. So I would go over the study guide very carefully and maybe take notes. So what I would do is I will go over the questions, and whatever, for example, on the first day, maybe for number 4, I'm not really sure about, I will be taking notes on a single document. So as you take the D2L quiz, instead of having all the slides, all the readings open, I would just refer to the notes so that you can quickly reference something, and so that you can finish everything on time. But also, if you're very prepared, the questions are, I'm sure you can finish within 1 hour or even half an hour if you're really quick. So the due date is going to be 11:59 p.m. on February the 28th. So any questions regarding the format of the midterm? And also, because you folks have been taking D2L quizzes, so I'm sure you know the format. So it's basically, once you open the quiz, you have to continue and finish. There's no way you can save your progress and coming back next time. So you just have to make sure you have, a slot of 1.5 hour and to get everything done. And we have nothing due this Wednesday. So this basically the due date's reminder is about next week, next Wednesday. So that because I'm not sure if everyone will be here on Wednesday next week. So I just want to mention the schedule quickly. So we have both Lab 4 and Lab 5 will be released later today. Both due on Wednesday, February the 24th. So far, I'm not really sure your progress regarding Lab 4 for the project data collection. So for now, I would say it's still the 24th, unless you make a request. So that part, if you're not so sure, we should talk about your project plan as soon as possible. And also your project data collection should be basically pre-processed. If you need a subset, you need to take a subset. You need to stack your layers together. And for the LiDAR data, you will need to really, make sure you have your data extracted and put together to cover your study area. So let me know if you folks have any questions. And once again, you can find the midterm study guide both on D2L and also in the chat. So today I would actually scroll down to the, basically to the image pre-processing. We have 7 questions for today. I think for just, for the sake of saving time, as we go over the new concepts for today, maybe you can, refer to the study guide for today so that you don't have to take time to review after class. We have a number of 7 questions today. And let me know if you folks have any questions. Okay, so today we're talking about image pre-processing. So once again, this diagram refers to the whole image processing and image collection process from data acquisition to data analysis. So after the midterm, we'll be focusing on data analysis. And today we're basically somewhere in the middle between F and G. We have data available, but we're not so ready for interpretation and analysis yet because we have to pre-process our data before the data are ready for further analysis. So regarding subset and mosaic, today we're going to focus on two other components of image pre-processing, but I would like to mention subset and mosaic today because it goes with image pre-processing. You will need to make sure your data are spatially ready before you can maybe classify or detect any changes. So regarding subset, if you have been doing GIS, it's probably something you are either do for your vector data or your raster data. So for subset, it's about extracting a smaller extent, a portion of your image to show only the region of interest. For example, we mentioned for Landsat data and also other images, each image seen covers a fixed area. So it's usually larger than, if you're looking at a city, it's usually larger than your study area. So the subset is about taking a portion of your image and to just zoom in to where you want to focus on. And it's important because with remote sensing, we're dealing with very large data sets. So if you don't really take a subset, everything you run, pre-processing or classify your image, is going to take a very long time. So sometimes after you put all your data together, your data set can get up to 8 gigabytes. So really, if you don't further reduce your data, some process can maybe take up to a few hours. I'm not sure if I shared, there was one process, it took me 7 hours to get ready. And that 7 hours is actually a trial and error experiments. So I had to really do the 7 hours multiple times. So that really just gives you an idea of, how long each image processing can take. And also that would depend on your hardware, the computer setup, whether you have a regular laptop or you have a workstation. But either way, subset can be helpful and also will really help people to focus on your study area, especially if you're doing some measurements. You don't want to have locations that are not relevant. And in addition to subsetting to only a rectangular area, you can also bring in your shapefile, maybe the city of Chicago or maybe the boundary of the metropolitan Chicago. So in that case, you can bring in your shapefile as a boundary and then delineate your study area that way. You can refer to the two videos I posted on D2L, goes with the lab 4 instructions, the last two videos on how to do subsetting. And sometimes you will have the opposite problem. For example, if your study area is large, if you're interested in studying the Great Lakes region, and also, by the way, we're looking at the two images at two different scales, and that's why you don't really see this large. But actually, you can see how many image scenes we need to cover the Great Lakes. So basically, mosaic refers to when you want to merge or combine multiple images to form a larger one in order to cover the study area. And also, when you mosaic, you will definitely want to mosaic multiple images from the same sensor, because otherwise, there will be different image resolutions in terms of spatial, radiometric, and also temporal. And another tricky part of mosaicing is, if you folks remember the idea of temporal resolution. So there's actually a, for Landsat 8, we have a 16-day revisit interval. So that means actually all your adjacent images will have a different time coverage, and that actually creates another challenge when you mosaic images. Sometimes, in one example, I actually mosaic images collected during different seasons, one from early spring and the other one from late summer, and the shades are entirely different. So when you merge things together, you can see a huge gap. So mosaic is trickier. So for those of you who need mosaic in your final project, I would be happy to work with you. And I posted the ERDA's field guide with, a few like a few specific instructions on, what the different mosaic mode means and how do you mosaic. So you can refer to the guide first, and we can also go over this together. There is a mosaicing dialog window in ERDA's Imagine where you can put different different images together and by maybe smooth or blending the different images. And also, if time allows, maybe we can try some mosaicing together just to show you folks, like how the interface looks like. But also for now, for your final project, if any of you need mosaic, let me know. So after subsidence mosaicing, and actually subsidence mosaic are corresponding to the first question within our study guide for today, the midterm review questions. So now we finished the first question: what is image subside and what is image mosaic? So let's talk about what we actually focus on today: the geometric correction and also radiometric correction. So overall, image preprocessing is about the processing procedures in order to improve image quality. So bad data in, bad data out. Really for remote sensing, the first step we want to make sure is after you collect your data, we want to make sure that our data is good and ready to go before you perform any further classification or change detection or any other more complex analysis. For example, maybe identifying objects or doing image segmentation that we'll be talking about after the midterm. So for image preprocessing, there are two major components, typically two major components. The first the first component is geometric preprocessing. And the second component is the radiometric preprocessing. So for geometric, it refers to spatially correct your data to bring your image into spatially, just make sure it's spatially registered with a reference map or another image in order to compare or in order to, extract correct geometric or spatial information. And for a radiometric, it's about adjusting the digital values or the pixel values to get rid of the additional effects of atmosphere, or there may be other reasons why you want to perform radiometric preprocessing, as we talked about more specific examples. So today we're going to focus on these two components of preprocessing. First of all, geometric, and second, radiometric. We'll talk about why and how, specifically focus on geometric, and you'll be practicing the procedures of doing a geometric preprocessing in Lab 5 using ERDA's Imagine. And also, we'll also talk about whether you need this two type of preprocessing in the final project, because depending on which data you use, you may or may not need preprocessing for this particular final project. But again, you still want to know the procedures because they're actually pretty common GIS analysis as well. So we'll go over the two components, and let me know if you have any questions. Feel free to unmute yourself or send the questions in the chat. And also you can refer to the study guide for today as we go over the different the different slides, and make sure you're you go over the 7 review questions along the way. So first of all, geometric preprocessing or geometric correction. I just want to mention a few cases or the reasons why you want to perform geometric correction. So the first example is actually from one of my, not very recent, but one of my recent research using nighttime photo from the International Space Station. Last time we mentioned for the International Space Station data, both nighttime image or daytime image, they're actually taken by hand using a Nikon camera. So, what is happening with the data is they're actually just regular photos when, the International Space Station renders the data through their website. So they're basically reducing the raw image or the compressed image, the original photo, the raw image directly. And you folks can see, because we're looking at Chicago, apparently the orientation is horizontal. So it's not really the north is facing your left. And actually the image came without any geographic information. So which means it's only a picture. Oh, even though you're looking at Chicago, but it's no different. It's no difference compared to your selfie. So basically when you bring this data into a GIS, it shows nowhere because there's no coordinate system. There's no geographic information defined for the image. There's nothing for you to really show the image in its correct spatial location. So the question is, how do we use the data in a GIS? And here comes geometric correction, geometric preprocessing. You can use this procedure to assign geographic information to the image data so that you can bring this data into your GIS and analyze the net levels and maybe further on, maybe compare the net levels for the different locations within Chicago and see how they're affecting the different areas, whether there's light pollution or whether there are some other phenomena you're looking at. And also, by the way, this procedure is also known as georeferencing. And actually, for those of you who have been looking for jobs, some specific job opportunities would include, georeferencing different historical images or topographic images. So georeferencing basically goes with geometric correction or geometric preprocessing. So make sure you also know the term. So georeferencing is about assigning geographic locations to your image data. So it's kind of you do geocoding with your address data, but georeferencing is specifically about how do you rubber shading a image into its correct geospatial location. And there may be some other reasons why you want to do a geometric correction. So I'm using a very extreme example. So once again, from International Space Station. So, in some cases, your image really doesn't have any geographic information, so that you have to do georeferencing in order to assign the location information or spatial information to your data. But in some other cases, distortion is a major problem. This image, I'm sure, because we are familiar with Chicago, and you can see this image is taken from a perspective. So which means, all these locations are not really planimetrically correct. So you have to perform geometric preprocessing in order to adjust all the spatial distortion. So those are the major reasons. So to summarize, the reasons why you want to do a geometric preprocessing is sometimes your data may not have any geometric or geographic coordinate system. There's no way to display your data into a GIS. So you have to apply georeferencing in order to assign the information, assign some coordinate systems. And also all the remotely sensed imagery are subject to geometric distortion. So we know for airborne data, of course, you can imagine the distortion happens with all the different motions of the planes, but also it's a common issue with satellite data as well. So there are different sources of error that contributes to the geometric distortions, the motion of the scanning system, the perspective of the sensor, and sometimes could be the terrain surface, the displacement between the top of the objects versus the base of the object. And you can imagine maybe a tall building in Chicago, and actually the problem is very common when you use a higher resolution data. And actually, maybe you folks have seen some examples from the first 2 labs we have done. The Iconos data, for trees, usually there's a shadow next to a tree. So if you place your cursor actually on the top of a shadow, your spectral signature will be inaccurate because you're not looking at a tree, you're actually looking at a shadow. So those problems are everywhere. And there are really a lot of reasons why you have to do geometric pre-processing. So if it's not really done by the image collection platform, it's almost required, because otherwise, the spatial information is all wrong, and then your measurements, your maps are going to be wrong as well. And also, in addition to the common source of errors, I also want to just bring up another possible source of error that I saw an article, the article's from 2016, and they're talking about actually continental drift. So Australia, by their record, has shifted 49 feet since 1994. So which can also be a source of geometric error, that if you want to compare 2 images, for example, if you're analyzing land cover change for Australia, between maybe 1990 and 2020, you will likely see this possible shift of locations, and which can further contribute to the geometric error. So many factors for you folks to consider, and I hope I'm justifying the reason why you want to do geometric correction, why it's so necessary, and that is corresponding to number 2 of our review question for today. Why is geometric correction of remotely sensed data necessary? Multiple reasons. So next, let's talk about how, or the specific steps of performing geometric correction based on image sampling. That is our number 3 for today for the review question list. So I'm going to use, again, the nighttime image as an example. And basically, if you imagine an image without any geometric information or without any geographic information, so what we really need to do is to assign coordinate information to the different locations, apparently. For example, one thing you can possibly do is, you can drive around the city with a GPS to measure the coordinates. For example, you can measure the end point of Navy Pier, and you can measure a few road intersections, or you can measure maybe the corner of Midway, or any other location objects, landmarks, or the corner of a park, the corner of a building, anything you can identify. You can just measure a few coordinate system and you assign them here. So that is definitely one way you can do, if you have the time and you can really make the effort and measure the locations accurately. But oftentimes, the geometric correction is done just in front of a computer by using a software. For example, you can do this in Artist Imagine. You can also do this in ArcGIS, and the tool is known as georeferencing in ArcGIS. But oftentimes, instead of driving around or collecting field data, because for remote sensing, the best part is you don't have to do field work. Well, you probably have to collect validation data, but you don't really have to survey the study area very carefully. For example, you can use remote sensing to study a place that you have never been to and just collecting data through Google Earth. So most of the time, so instead of driving around, we'll be using a reference map with correct geographic information. So what we really need in addition to the data to be pre-processed, to be corrected, we need a reference. So our reference map need to be planimetrically correct. That usually you can get data from USGS, and they have those georeferenced topographic data that you can use as a reference. And there may be also corrected data for georeferencing purposes as well. And also some other times, if your purpose is only just going to do a quick map, you can also use the base map within your program. ERDAS and ArcGIS both allows you to add a base map. You can also just bring in Google Map as a reference to collect the geographic information. So overall, there are 2 steps for performing a geometric correction. The first step is about selecting ground control points. And the second step is about image resampling. And we're going to practice the 2 steps in lab 5 so that you have more hands-on experience and you can really talk about the procedures. So the 2 steps are corresponding to number 3 of our review question for today. What are the steps of performing geometric correction? So it's going to take a few slides as we go through the steps, because we need to focus on just talk about how to select good ground control points, the GCPs. And second step, we're also going to make sense of the 3 different image resampling techniques and methods. So it's going to take a while and also a few slides. So make sure you're on track, and also let me know if you folks have any questions. So let's first talk about the first steps, but step 1 about selecting ground control points. So let me zoom in a little bit, and here I'm looking for your input. Speaking of, so let me explain what the GCPs do specifically. So for selecting the ground control points, or the GCPs, so essentially the idea is about we're trying to match the image to be corrected to the reference map. So the GCPs are actually pairs of locations that you can easily identify from both images. Given the specific image resolution and also the reference images resolution, locations you can easily identify from both images, so that you can use those pairs of locations as reference. For example, you identify 1 pair and 2 pairs and 3 pairs, and so that you can spatially match your data without any geographic information or with incorrect geographic information to the reference image. So essentially, the first step is about selecting matching pairs in terms of their corresponding geographic locations. So I hope that makes sense. And right now, I'm just looking for, because you folks can possibly annotate through on top of your screen. There should be maybe a more, and you can select annotate. And what I'm looking for is, given the idea of selecting ground control points, what do you think are some good, or where are the good the GCP locations that you can select from both images? You can also unmute yourself if you want to just talk about the locations, or you can use your annotate tool to start drawing pairs of locations. Does that make sense? So basically selecting pairs of locations that you can easily identify from both images. And I can also zoom in if you if that helps. So this is our nighttime image to be corrected. And this is our reference map. And right now we're on Prezi. So as I zoom in, it's just only gonna get blurry. But technically, as you zoom in your program, it can zoom into the individual pixels of your image data. Any ideas on possible candidates of GCPs? And this is actually what you folks will be doing in lab 5, that you have to select your own ground control points. Okay, I'm seeing a few. Sorry, I think I shouldn't move, but okay. So let's just use whatever portion available here to, sorry there, I probably should move the image, but I guess as I move, this locations will be off, but I get the idea. Can we also select the corresponding GCPs on here? If your locations are here, okay. Okay, so I get the idea. So we're generally just trying to match the rough locations, and I saw the intersections, and I'm assuming here is about navy here, where you can identify. So so my only comment may be, just roughly speaking, is about O'Hare. So I would say this location, this pair of location, need to be more precise, because the idea of matching coordinates is we do want to go down to pixel level, as precise as possible. So this one, this particular location, I would maybe move to, wherever you can identify a pixel size location, maybe the the intersections, or the one particular edge or corner of O'Hare. So that would help you reduce the possible errors. Okay, great. Let me clear all for now, and then we can talk about the general ideas. I need to clear myself. So for selecting ground control points, it's really about selecting pairs of locations on both your raw image and your reference image. And also the key is to make sure you can go very precise, ideally under a pixel. So no more than 1 pixel, otherwise you will have a lot of trouble. Because I saw some corrected images which are totally distorting the original image, or like basically twisting. So you will want to be really precise and very accurate. And also some of these locations, I didn't really see anyone used midway, but actually when I corrected this particular image, every single time I started with navy pier, and my second point is usually a corner of midway. Just so that, because it's really an easily identifiable location from this nighttime image. I don't really see, the buildings are not very clear, but it's only like bright spots or dark areas. So I found midway to be a really easy location to identify. And the third pair I just used, as you folks used, I think this was identified. So, road intersections can be a very good candidate pair. So once again, for selecting ground control points, it's about selecting pairs of locations. For example, if we say 3 pairs, it's actually about 3 on each image, 6 locations in total. So make sure you don't get confused. Whenever you're selecting one from your raw image, you have to select the corresponding location from your reference image. Otherwise, there's no way we can correct or georeference your image. So basically, all these pairs will help you establish this model or geometric relationship, so that you can further in the second step to resample your data. So just a quick summary of some of the considerations when you select your ground control points. So first of all, your ground control points should be as small as a single pixel. So in the example, I wasn't able to really zoom in very closely, but when you select your ground control points, you will really want to zoom in until you see the individual pixels within your image. If you just, okay, let me just roughly select a location, you won't be able to meet the requirements, because overall, we want our total error to be as small as under half of a pixel, or even actually most of the case I can reach maybe like 0.0003 pixels. That would be ideal. Otherwise, you're only going to mess up the geographic location. So as small as a single pixel, zoom in, look things very closely, but also as you folks can possibly imagine, or you can use Lab 5 as an example to just picture the idea. So Lab 5, we're using Landsat, which has a resolution of 30 by 30 meter pixel size. And the problem is, 30 by 30 usually means the corner of a building or the road intersections are really gonna get really blurry, which can be tricky, but also, that's part of the process you have to get used to. It won't be 100% accurate, but you can try your best to achieve the highest accuracy, the precision. And some of the good candidates of GCP pairs include road intersections, maybe the edge of a parcel, the corner of a parcel, maybe the corner of a building, could be the stream junctions if you're really comparing two images from the same year, but also be careful when you are using a reference image from a different year. So natural features can change their locations. There may be a change of courses, landmarks, many different candidates for you. So again, I think the first 2 points that go together, be accurate, be precise, as small as possible, zoom in as you can. And overall, in terms of the distribution of your GCPs, so apparently we need a number of GCP locations for you to match your raw image to the reference, because if you only match one pair, there's no way you can build a model. So usually, depending on the model you choose, you will need a different number of ground control points. So the idea of, in terms of the overall distribution of your ground control points is that you have to make sure your ground control points, they're dispersed throughout your study area or throughout the image. And you do want to cover the center and also cover the edge of your image so that they form a polygon, not on the same line, because, given all the different mathematical models we're going to apply, if all your points are on the same line, for example, if somehow they're all on the same highway at different intersections, it still won't really allow you to match the two images very nicely. So you can think about the idea as selecting good samples. When you're trying to select representative samples from your study area, you probably want to have a little bit in the different locations so that they're dispersed and they have good coverage in your study area. And also, the question is also how many ground control points we need. Apparently you don't want to spend the whole year selecting millions of ground control points. So actually, we don't really need a large number. So according to past research, so some authors are recommending, somewhere between, I would say between 14 and 20 ground control points. And of course, that would depend on how large of your study area is and also the resolution. So my personal experience is you definitely don't want to go beyond 20. So actually, the problem is within your image, within an urban area, maybe a more natural area, speaking of the good candidates, road intersections, or corner of a building, corner of a park, of a parcel, some landmarks, stream junctions, they're only going to be a limited number of good ground control points that you can identify, as small as a single pixel. So, I think you just exhausted all your good candidates. Maybe you're trying to select more, but the more you have, they're only going to introduce more errors. So that is really the justification of why, sometimes you don't really need too many ground control points. So there are cases I only did 14 ground control points, and the author recommend 16 ground control points, so that you just only have a number, but the number, the limited number of ground control points, they're very accurate, very precise, and they're enough for you to build your model to transforming your raw data into its correct geometric location. So for best accuracy, more is not necessarily better. So, the author recommends 16, but I would roughly say in practice, you will want to be somewhere like maybe between 14 and 20, or sometimes maybe 12 will give you a good, a total error atom in terms of the total model performance. You will see how do we measure the model performance in lab 5. Actually, in ERDAS Imagine, and also in pretty much all the program GIS, they will report a X error and a Y error and a total error. So what you want to do is just basically you're trying to ensure your total error atom is as small as possible. And of course, you're pretty sure that your corresponding GCP pairs, they are matching each other, like in terms of their corresponding locations. And here is just a screen capture from lab 5. And this is the multi-point geometric correction dialog, which will be basically floating on top of your regular ERDAS Imagine. So you can read, the headers. So this image is our raw input image to be pre-processed, to be geometrically corrected. And we're looking at Pensacola in Florida in this particular lab. And even if you have never been to Pensacola, I'm sure once you're seeing the image, it will be easy for you to identify some locations. The structure is pretty simple to follow. For example, right now I'm only selecting one pair of locations. So once again, speaking of ground control points, we're actually talking about pairs of locations that are easily identifiable from both your input and your reference. And in lab 5, we're using a topographic map from USGS as our reference, as our geometric coordinate reference information. So you're selecting one pair of location and they're roughly matched. And you can see the 30 by 30 meter resolution is tricky. When you zoom in, that you see everything gets really blurry. However, you have to still try your best to match their spatial coordinates. And once you have selected each pair, you will be able to observe the locations. For example, right now we have number 1. So GCP1 means one pair. So you have X input and Y input, which refers to the location of these points I'm highlighting here from the input data, the raw image to be corrected. And you also have the X reference and Y reference, which specify the location on your reference image. And overall, so now basically here you have your first pair ready. And in lab 5, the minimum requirement is you have to select at least 6 pairs. So you have to really do another 5 more pairs or 10 points in total. And matching location, you can change their color. And once you have, given the model we chose in this particular lab, once you have your 4th point, the program will automatically pop up a location on your reference, which actually because your model can estimate and can also predict, and you'll be able to observe a total error atom at the corner here, so that you can see your model performance, and you can also observe your X residual, Y residual, your RMS error for each pair. So wherever you see a large one as an indicator of this particular point is wrong. So, it's a process. So basically you have to really maybe go back and forth. If you're, like seeing the too large of an error, you have to go back and maybe delete one pair or fix one pair. So this program would also allow you to adjust locations. You can highlight, the ground control points and move things around, and to make adjustment, you can right click to delete some points. So that's just an overview of lab 5 that we are using. geometric correction, this dialog from Earth Imagine to do the georeferencing. And in ArcGIS Pro, the corresponding tool is called georeferencing. So the idea is very similar. And I also used QGIS for doing the same thing. They're all pretty much the same idea. You have a reference, you have an input, and you're selecting points from each, and you're seeing the corresponding table, and for you to observe your total error. And you can compare things side by side, and finally you can georeference your image. And actually, for my first GIS internship, I did some georeferencing. Well, actually, I did a bunch of different things during my first internship with a research organization back in Florida. So, so one part of the job was basically georeferencing some of their historical topographic maps. And in that case, we were doing some simple georeferencing because we know within each topographic map, the locational information is pretty accurate. So what we were doing is basically matching the corner of each topographic map to the reference so that we can display the topographic map to the correct location instead of only like the scanned papers or the scanned photos. There are some, there are a lot of use beyond remote sensing that you'll be applying the procedures of geometric correction and selecting ground control points. So we're not done yet with geometric correction. So there's a second step of geometric correction, which is known as resampling. But also, if you want to take a quick look at your study guide, we have finished. We're not done yet for question 3, but we're done with question 4 regarding what are GCPs and what are the considerations in selecting good GCPs for geometric correction of image data. And now we're going to talk about question 5, and also that way we can also finish question 3. So question 5 is about the second step of geometric correction, which is image resampling. There are 3 different resampling methods. So back here, back to the slides, second step of geometric correction. So now imagine we have a good number of GCP pairs, ground control points pairs, maybe 10 or maybe 15. So now we're ready to go. So you have carefully selected all the GCP pairs. However, you will have to perform image resampling in order to finally correct your raw data into the correct geographic information. So the idea is the ground control points is only to build the model, like to match the corresponding locations from your raw image into the reference. Image resampling is actually the procedure, the second step to determine how to estimate the values in the corrected image based on your input, based on the pixel values in the uncorrected image. So there are 3 techniques, 3 methods in total. And there are nearest neighbor, bilinear interpolation, and cubic convolution. So there are the 3 methods of doing this estimation. So now you have your correct location. It's kind of like a placeholder where you have a certain number of pixels depending on the cell size you choose. You can actually change the cell size, essentially the resolution, to be the same or to be the different. And the resampling methods will determine how to assign the values from your source, from your raw input data into your final corrected placeholder, the grid of cells. So let me just show you a comparison first, and then we'll go over how the 3 different image resampling methods work. So just a quick idea, but I'm not really trying to indicate anything in terms of accuracy or uses, but I want to just give you a visual comparison here. So among the 3, so we are comparing the results using the same set of ground control points, same number and same locations, but we're taking different image resampling methods for the second step. And the first one is from nearest neighbor, and the second one is from bilinear interpolation, and the third one is from cubic convolution. So just to quickly compare the 3 results visually, which one do you see? Which one do you observe a smoother pattern? And which one is most, sorry?
Bilinear. They all kind of look blurry here, but it seems like bilinear is smoothest.
Okay. And which one is more, is the most pixelated?
Nearest neighbor on my screen.
Okay, yeah, that's very accurate on your screen. On my screen, it's also nearest neighbor, and also I would agree that nearest neighbor is the most pixelated. But also I can see it's maybe hard to observe. But if we focus on, I guess it depends on how do you define smoothness. So technically, actually, the cubic convolution, depending on the mathematic operation, the cubic convolution gives us the smoothest. So basically, I can see why is Rob, you were saying it's maybe bilinear, because I can see, if you compare the boundary seems to be clean, maybe. So it's okay. It just, I guess it depends on how we're, and there's highlighting. Thanks. So let me clear all of our drawings. But either way, so let's just go over how the different methods work. And also, once again, by, the pattern, it's not really suggesting, you have to go back to my spotlight view. So the pattern doesn't necessarily suggest which one is better or which one is more accurate. It actually depends on, once again, it depends on the purpose, and also depends on your study area. So first of all, for the nearest neighbor resampling, the idea is, let's first look at the diagram here. Sorry, I'm trying to zoom in, but it's every time it's just popping up to the original image. I hope it's clear, or if you can zoom in, maybe using the Prezi on your own screen. So once again, for the image resampling, it's actually about assigning or estimating the pixel values. Once you have, the ground control points, you probably have a placeholder that the solid grid here is our target, our corrected image, the final results. The dashed line refers to, in this diagram, refers to the original image. So the nearest neighbor, basically for each cell within the corrected image, make sure you don't get confused. For a corrected image, we're talking about the solid line grid. For the nearest neighbor, the solid line grid, each cell will take the pixel value from whichever location from the original image, whichever cell that is closest, that is nearest to this particular target cell, if I'm clear. For example, for this grid cell we're looking at here, this grid cell intersects or overlaps with 4 input cells. But if you compare the 4, apparently this one takes majority, or which we consider as the nearest. So this original pixel value from the source image, from the original image, was assigned to the target image or to this correct image cell. So we're doing this for every single location. For example, the top corner pixel, this target pixel will get a value from apparently this cell where it's nearest and where it overlaps the most. So that's where the name of nearest neighbor came from. They're taking a value from the nearest neighbor from the source image. And also another very important point I want to make here is nearest neighbor resampling is the only method, once again, among the 3, nearest neighbor is the only method that is able to preserve the original pixel values, because they're not really doing any modeling or any estimation. So they're just taking whichever closest, whichever nearest to the target, just taking the original value. You're not really making anything up. You're not taking the average. You're preserving the original pixel value, which actually the reason that makes nearest neighbor one of the most popular method, and that is what we use in lab 5. Actually, when you run your resampling, you will choose between the 3 different methods. You can choose nearest neighbor by linear interpolation or cubic convolution. So we chose nearest neighbor. So the best, basically the pro of nearest neighbor is it preserves the original pixel value. However, one of the problem of nearest neighbor is, if there's a large displacement or a large geometric difference, there may be noticeable positional errors from your source and your target. And this is also why you're seeing a lot of pixelated, because we're not smoothing anything out. We're taking the original value, even if they're really not smoothing or they're not really matching the neighbors. There's also just going to take the original value to the target. However, nearest neighbor is very nice whenever your study area is relatively flat. So in Chicago or in Pensacola, Florida, nearest neighbor is definitely the method you should be using. Nearest neighbor is recommended whenever your study area is flat and there's not really much of displacement or terrain introduced errors, and they're really flat, and when you correct data, it's basically just matching things up. So flat area, nearest neighbor. And let's also talk about bilinear interpolation. Even if we're not using it in the lab, you may be using it for your final project if you're looking at a relatively mountainous area. So bilinear interpolation, instead of assigning the original values from the nearest neighbor, bilinear interpolation will take the 4 neighbors and take the average. For example, for this light gray target pixel, they're taking the average between the 4 neighboring pixels from the original image, and they're creating the new pixel value. So they're taking an average, which means they're not preserving the original pixel value. And however, by taking the average, it's actually creating a smoother look or a natural look, less blocky, less pixelated, but all the original pixel values are lost, which can be a problem because we're talking about remote sensor data. We're using the data, so you don't really want to, if your study area is flat, you will try to avoid of making up data yourself because all your original values are lost by using bilinear interpolation. However, if your study area is highly mountainous, bilinear interpolation can actually be very accurate, but be more accurate than nearest neighbor because there are displacements naturally within the image. So bilinear interpolation can actually help you solve the problem, the spatial mismatch. And cubic convolution is actually a more extreme version of bilinear interpolation. So in this case, instead of only taking the 4 nearest neighbor, they're taking a number of 16 neighbor pixels and taking the average. So which makes cubic convolution the most average process, which once again, they don't preserve the original pixel value. They're taking the average and weighting them and create the new value for the target pixel. So cubic convolution is once again also works for highly mountainous area. So in the lab, we're going to do nearest neighbor for the Pensacola downtown region. So any questions regarding the geometric correction? So we've talked about the 2 steps of selecting GCPs and image resampling. And so now we finished question 1 through 5 in the list. And if there's no question, I'm going to talk about.
Sorry.
Simone.
For the binary like the binary interpolation. Could
Yeah.
you? So what? Sorry, I missed. Besides taking the four uh, neighboring pixels and creating a new pixel value, what is an example where it would be used for?
In a mountainous area that you're, so in terms of example, it basically is the second step of your image resampling. So if you have a mountainous area where the image collection may displace, the different objects, so bilinear interpolation can help you smooth out your land cover or the pixel values. So both bilinear interpolation and cubic convolution, therefore mountainous areas, hilly regions.
Okay.
If that answers your question, Simone.
Yeah, because I know the nearest neighbor is used for just like clustering, correct?
No, that's the different idea. So nearest neighbor is for, so again, here we're talking about image resampling. So we're not really
Right.
talking about any statistics or anything. So this,
Okay.
right, this step is about the second step of image, geometric correction. So it's only one of the methods of assigning the values. So, for those of you who has taken statistics, just, don't get confused. We're not really talking about that. The idea is similar, but we're talking about image resampling.
Okay. Thank you.
When you say mountainous, does that apply to like any DEMs like of like lakes and oceans too? Just anything with elevation changes, basically. So would
Uh,
you?
right. So I would, I'm more referring to wherever that you see, well, basically the DM, wherever you see, and also that is the scenario where you will be observing, and actually in the mountainous area, you can see the pixel values, they differ. For example, the shadow part and also, the mountain top, and you can see the displacement very clearly.
Okay.
Yeah, it's basically, we're talking about
Okay.
the ground surface. Okay, and okay, we have 10 minutes left. Let's talk about the second component, which will be quick on radiometric preprocessing. So now we can focus on number 6 and 7. Also go back to number 5 of the review list, which method does not alter the original pixel values. That will be nearest neighbor. So that's the only method among the three that can preserve the original pixel value. So next, let's talk about radiometric preprocessing. So radiometric, as we know, radiometric resolution refers to the different quantification levels, the different level of brightness. So radiometric preprocessing is about basically the preprocessing or the correction procedure to adjust the brightness values of an image. So now we're talking about actually adjusting the pixel values. And also I'm going to talk about why and how. So there are different reasons why you want to perform radiometric preprocessing. So whenever you're altering, just basically trying to change the pixel values or adjusting the brightness levels, you're performing radiometric preprocessing. For example, we talked about Landsat 7 after May the 31st, 2003, there was this SLC failure, the gaps within your image. So, sometimes you may perform radiometric preprocessing to correct for a sensor malfunction. So the Landsat 7 ETM Plus was an example. And sometimes, people may consider removing the dense cloud covers to be another process of radiometric preprocessing, because when you classify your image, you're interested in the ground condition. Definitely you want to get rid of the cloud covers. So today we're actually going to focus on one particular example under the bigger category of radiometric preprocessing, which is known as the atmospheric correction. So basically this particular component refers to the procedure to adjust the values to compensate for atmospheric degradation. So I'm going to give you some examples because it's probably hard to imagine. Have you folks seen a device like this? I'm assuming maybe a no, or unless for those of you who have taken some physics class. But do you see this graph familiar?
Yeah.
Yeah. So it's definitely something we have done before. That's the spectral signature. And this device is actually handheld, and it's called a field spectral radiometer, which is for you to measure the spectral signature of different ground objects, the spectral signature of different ground features by a very close proximity, which also represents the true surface reflectance, the spectral signature of the different ground covers. So once we have the device, and actually this second graph, I'm showing you a comparison of two spectral signature patterns. And one pattern is representing the actual surface reflectance collected by using the handheld device, the field spectral radiometer. And the light gray pattern represents the pattern collected from the satellite data. Apparently they're different, right? And we know, well, actually the surface pattern should be the true pattern, because once again, whenever we're doing image analysis, we're interested in the ground color. So we want this. We want the solid dark black line here. However, so far, what we have been using iconas or originally the older data of Landsat, what you're getting from the satellite directly is the lighter gray line, which is really not ideal because they're different, which could likely, bring in some errors when you classify your data, when you analyze the patterns, the different ground objects. So there's a problem. So whenever you're collecting data through the sensor, the satellite, or the airborne, it's the same idea. There's a difference between the two signatures. And this difference is actually caused by atmospheric scattering and absorption in the image. And also, generally speaking, I'm not sure if you folks can see a pattern. So generally speaking, the difference is larger at the lower range of the spectrum compared to the longer range. We actually talked about, longer range has a better penetration power, can penetrate through a cloud cover and also all the different dusty, atmospheric conditions. And that actually another proof or an example of why, this is the case. Actually, in the lower range, the visible portion where you really see a lot of effect from the atmospheric scattering and absorption. So really, this atmospheric correction is about getting rid of the difference, detecting the difference, and measure the difference and get rid of the difference so that we have the true ground surface reflectance for further analysis. So it just, once again, more example on, how the difference was measured. Whenever you're collecting data by a sensor, whether it's airborne or satellite-borne data, you're collecting both the actual signal from the Earth's surface, but also you're collecting some additional noise, some additional data from atmospheric scattering, which is something you don't want to get rid of. One specific example can be when you look at a pixel value that is, for example, 56, and there are actually two components. You want the 45, so you will have to figure out a way to detect the 11 so that you can get rid of the 11 and to get the true surface reflectance. So what you're really trying to do from the original diagram is you're really trying to bring down the original satellite measured reflectance to the surface reflectance, and you want to get rid of the atmospheric scattering, and so that you can use true data to measure the ground surface. So far, there are many complex models and also actually some programs developed for doing doing this atmospheric correction by modeling the different ground conditions. So let's just, because we only have 3 minutes left, so I just want to quickly mention one simple method. And we finished also the question 6. What are the effects of atmospheric scattering on remote sensing data collection? So basically, the difference between your surface reflectance versus your satellite reflectance. So now let's look at number 7. So for the simple approach, actually, one simple approach is known as the dark object subtraction, which is to, first of all, you identify a very dark object from the image, from your image scene, which, for example, maybe you're thinking about water. Of course, water can be an example, and shadows can be an example. And for those very dark objects, you can assume their reflectance, their brightness is supposed to be 0. However, we talked about there is the scattering effect from the atmosphere, which actually will bring up their pixel value. So basically, what we do is, for example, you look at your a very dark water area or a very dark shadow, and you analyze the pixel value. For example, you found out roughly, the dark area, somehow they're supposed to be 0. However, they're all having a pixel value that is around 15, for example. And then you can sort of simply assume, okay, this 15 is the added atmospheric correction. And then what you do is basically you do a subtraction. You subtract this value from every single pixel within your image, within the same band. And so that essentially what you do is you basically move your histogram towards 0, because your histogram, the pixel values, the lowest value is supposed to be 0. However, somehow you can see it's actually 20 here. So what we do is we're taking this 20 as added brightness of atmosphere. We move the pixel, the whole histogram towards 0 to bring it down linearly. So this is one of the simple approach that is known as the histogram minimum method, or the dark object subtraction technique. So basically, you just get rid of the lowest brightness value within a given band, and so that you can just reduce the effect. That's a very simple approach based on a simple assumption. And also there are, regression techniques developed, and some people are using the different, by considering the solar zenith angle, and by considering the different solar conditions. You actually use the cost model before, when I did my actually very first remote sensing publication. And there are also programs available, the different ways of modeling atmospheric condition. And actually, when you download your data, if you're interested, I do recommend maybe take a look at your metadata. Your metadata will contain the specific atmospheric conditions, and including the solar zenith data, the solar direction information, which can help you model the specific atmospheric condition during the time and day when your image data was collected. Okay, so I think I'm running over time by 1 minute. That's all I have today. And we're meeting this Wednesday to work on lab 5. And also for now, I would say still the lab 4 due date is 24th. But let me know if you need an extension. But also, just hopefully we can get this thing going without waiting until the last minute. So the study guide is available, and we're doing a review on Monday next week, which is, well, of course, optional. So I made this Slido, which once again you can scan the QR code to submit a question, or you can go to slido.com and enter the code of 20549. I'm making this thing available until Thursday. So if you have something later today, you can keep submitting, or tomorrow or Wednesday. So Monday, we're going to go over your questions if there are any. Okay, it's also answered. If you have more questions that you want us to review together, so let me know and we can do it on Monday. Otherwise, I may be just hosting a session to answer your questions individually. So again, please use the study guides to review everything so that you can finish the test on time because you only have 90 minutes in total, which again, should be sufficient if you're ready to go, but there's just no time for you to review every single one or check every single thing. It'll be really rush for the 90 minutes to do all this. Okay. All right. I'm hosting my office hours now if you want to stay. Otherwise, I'll be seeing you later this week or next Monday.